Bismillahirrahmanirrahim. Dear students, today we are going to discuss a new series of reactions which belong to the carbon oxygen bond formation. The first reaction today we are going to discuss from this series is Keck Macrolactonization. This reaction is basically about the formation of ester linkage, cyclic ester, from carboxylic acids which also bear hydroxy group. That is, the substrate is hydroxy carboxylic acid, which is converted into ester linkage by interlinking these two functionalities, that is carboxylic acid and hydroxy functionality within the same molecule, and so we get a cyclic ring type structure having ester linkage, and these compounds are known as lactones. And so macrolactonization means this cyclic ring can be 6 membered, 7 membered, 8 or more number of carbon atoms can be in the cyclic ring. So therefore it is also termed as macrolactone, and the process macrolactonization, and this process was the introduction by the Keck scientist, and so we name this reaction as Keck Macrolactonization reaction. Today's lecture about Keck macrolactonization includes simple general introduction to Keck macrolactonization, then the explanation of the mechanism step by step, and then general features of this macrolactonization process, and in the end we shall discuss some synthetic applications of this reaction. There will be some revision of the basic overall mechanisms also, in addition to step by step mechanism. The basic reaction, the base of this Keck macrolactonization reaction was the use of hydroxy carboxylic acids in the presence of DCC, DMAP, DMAP.HCI, chloroform, and we get the product of lactone formation. Lactone were the cyclic esters which are generally known as lactone, and macrolactone are the cyclic ester having large size of the cyclic ring. So the Keck macrolactonization reaction involve the formation of medium and large ring lactones from hydroxy carboxylic acids, and it uses dialkyl carbodiamide and amine hydrogen chloride and amine base. In this case, dimethylaminopiridine is used as a simple base, and also its salt form with HCl is used in the reaction. Here you can see also the structures of these moieties, that is DCC. In place of DCC we can use EDCl also. The structure of both moieties is shown here, and DMP is the dimethylaminopiridine, and its salt form which is protonated at the lone pair of nitrogen of heterocyclic pyridine ring instead of the nitrogen of dimethyl amino group present in the molecule, and this protonated DMAP is also used in the reaction. In the first lecture we have discussed about the formation of lactone from this mechanism 1, but here I am going to give you some critical view of this mechanism. The first step is clear, okay, the formation of activated ester by the interaction of hydroxy carboxylic acid and carbodiamide. The proton transfer it can be from carboxylic acid, it can be from some other protonating species present in the medium, so this thing is acceptable. On the second step, when this activated ester is shown to interact with the DMAP.HCI, protonated dimethylaminopiridine, Here you can see the attack is going to be from the lone pair of hydroxy of carboxylic ester on the proton from protonated dimethylaminopiridine. If we see some critical, then you can see the nitrogen, which is also double bonded with carbon, has lone pair. And if we compare the nucleophilic character of this oxygen bearing 2 lone pair and the nitrogen bearing 1 lone pair, and also both are sp2, sp2, nitrogen sp2 hybridized, but oxygen in case of carbonyl is mostly termed as sp hybridized. Number 1. Number 2, the nucleophilic character of nitrogen is greater as compared to that of oxygen, so the lone pair of this C double bond and moiety functionality should attack on the proton instead of this lone pair of this carbonyl functionality. Also, in addition to these 2 lone pair, there are present 1 lone pair on the single bonded nitrogen amine NH, and 2 lone pair on the oxygen of this ester moiety. Here we can say the lone pair of the 2 lone pair of this oxygen of ester functionality is going to resonate towards this carbonyl functionality or that C double bond N functionality. So it is not available for the attack. And similarly, the lone pair of NH is also moving towards the C double bond N functionality and is in the position of resonance, so it may be unavailable for the protonation. But the hydroxy group bearing 2 lone pair is available, can interact or can act as a nucleophile. Here this thing is looking to be awkward in this reaction step. And then the remaining parts we have discussed in the last lecture, how the hydroxy attacks on the carbonyl and how ring is formed, and we get the byproduct of N prime dialkyl urea along with the main product lactone formation. This is the second mechanism which we have discussed in detail in the first lecture. Here I am going to discuss also 1 or 2 points which regarding this mechanism. First step is the protonation step, and this proton can come from the carboxylic acid present in the medium, or can come from the HCl or protonated amine, and we get the activated ester, and in the next step of the attack of pyridine on the carbonyl. Here was the question, why this pyridine attacks on this carbonyl, carbon of this carbonyl functionality instead of the carbon of that C double bond N functionality. I will explain this on the stepwise mechanism also, this thing also. Second question is which is going to be critical on this mechanism, that is, after the attack of this pyridine we get the final intermediate in which this now pyridine nitrogen is getting the positive charge. We know that here pyridine positive charge means because of 4 bonds of nitrogen we are giving it apparently positive charge, but this positive charge can be counterbalanced, or you can say should be removed by the movement of the double bond on the nitrogen, and the benzene ring should be like that of co-unknown structure, and it should move in such a way. But here in this mechanism you are seeing the pyridine structure which is only shown with positive charge. I think that the more stable form is that in which this ring will contain 2 double bonds, and the dimethyl amino moiety will contain carbon nitrogen double bond and positive charge on this nitrogen, which is easily counterbalanced by the negatively charged species. This is the third step type of mechanism which we have discussed in the first lecture also, and this mechanism was looking to be too good as compared to the first two lectures, and we shall discuss next the stepwise mechanism also, which is mostly based on this step 3 mechanism, but at some instances there is some changes in the stepwise mechanism also. Here is the first step of this reaction, in which the hydroxy carboxylic acid is going to interact with DCC. Here in this case we are taking dicyclohexyl carbodiamide DCC. Here you can see the structure of DCC, in which both of the nitrogens bearing two lone pairs and the centralized carbon is attached with these two nitrogen through two double bonds, so it is too much electrophilic in character, and the nitrogen bearing the lone pair, one of the nitrogen can attack on the proton of the carboxylic acid, which is having partial positive charge, and the neighboring oxygen has partial negative charge, and the double oxygen hydrogen single bond is broken, and the two electrons are moved towards the oxygen, making it negatively charged, and this negatively charged nucleophilic oxygen attacks on the electrophilic center of this carbodiamide carbon, and at the same time carbon nitrogen double bond is broken, and this carbon nitrogen bond is broken towards that carbon which was previously protonated and found 4 bonds, and now it will become with 3 bonds. So we get this activated ester, in which here you can see the ester linkage is present, but the oxygen of this ester is further attached to a functionality which bears carbon nitrogen double bond and also carbon nitrogen single bond at the same time. Here another thing is shown in red color, that is n number of carbon atom can be 1 or greater than 1. If 1, then we will get the 6 member ring. If it is greater than 1, then we will get the large macrocyclic ring. So basically no doubt simple small rings can also be generated by using this technique, this Keck Macrolactonization method, but generally this reaction is used for the macrocyclic lactone formation. Here is the step 2 in which this previously synthesized activated ester is now treated with dimethyl aminopyridine HCl hydrochloride, that is protonated amine. Here you can see the lone pair of this C double bond and sp2 hybridized nitrogen is going to attack on the proton of this protonated amine, and it is now protonated with NH having nitrogen with positive charge on the product side, and this positive charge is counterbalanced by the negatively charged chloride which was previously attached with the protonated amine, and the byproduct is the neutral amine. Here is the question. First question is that why this lone pair of this nitrogen double bonded nitrogen is involved in this nucleophilic attack instead of the two lone pairs of oxygen of double bonded oxygen. First question. Second question is that in addition to these double bonded nitrogen and double bonded oxygen, there are present single bonded nitrogen and single bonded oxygen, and the lone pair of that nitrogen and that oxygen should attack and should be more nucleophilic as compared to sp3 hybridized functionalities, or these atoms nitrogen or oxygen should be more nucleophilic as compared to sp2 hybridized or sp hybridized. So first thing Why when we are going to compare that double bonded nitrogen and double bonded oxygen, then you will know that both categories are looking to be same, but in case of hybridization we know that nitrogen is thought to be sp2 hybridized, but oxygen is thought to be sp hybridized. Number one difference, and sp2 hybridized will be more nucleophilic as compared to sp. Number two, nitrogen has large size, and we know that nitrogen is more nucleophilic as compared to oxygen, so the lone pair of this nitrogen will act as nucleophilic as compared to double bonded oxygen. Now if we compare the single bonded oxygen of ester and single bonded nitrogen or sp3 hybridized nitrogen, then you can see that the lone pair of this nitrogen is going to be resonate towards this carbon double bond nitrogen. Single bonded nitrogen, that is sp3 hybridized nitrogen lone pair, is going to resonate towards the carbon double bond nitrogen, and in this resonance you will see that there will be double bond between this sp3 hybridized nitrogen and carbon, and the carbon nitrogen bond will become single, and nitrogen will get a negative charge, and negatively charged nitrogen is more nucleophilic as compared to a neutral one. First thing is here. Second thing, the oxygen of this ester functionality has two lone pair, but in the similar basis the lone pair of this oxygen also are moving towards the carbonyl C double bond O or towards the C double bond N. So the lone pair of this single bonded oxygen are also not available for the nucleophilic attack, because they are resonating towards the C double bond O or C double bond N. Next, there is the third oxygen is also in the form of hydroxy, which is also has two lone pair, that is oxygen hydroxy, or oxygen of this hydroxy group has two lone pair, which can also act as in the form of protonation, but the case is the similar, that this hydroxy will be neutral, although it is sp3 hybridized, but it is neutral species, but that nitrogen which is going to get the proton is negatively charged due to resonating structure, and so it will be most active for this step of protonation. After this protonation, the next step is the attack of the neutral dimethylamino on this ester functionality. Here you can see the moving arrows, that is the dimethyl lone pair of nitrogen of dimethylamino group is going to move towards the benzene ring, and then the double bond between carbon number 1 and 2 of benzene ring is going to move towards carbon number 2 and 3, and the double bond between carbon number 3 and 4 is going to move towards nitrogen, and then this nitrogen is going to attack on the carbonyl carbon of the ester linkage, and the carbon oxygen double bond is broken into single bond, and oxygen gets the negative charge. On the next step, you see this negative charge of oxygen comes back, and then the neighboring carbon oxygen single bond is broken, and this single bond sigma electrons are moving towards the next carbon oxygen single bond, which has become now double bond, and the carbon nitrogen double bond has now become the single bond. Nitrogen is the positive charge nitrogen has also finished due to formation of single bond here, and now this Cl minus will be counterbalancing the positive charge of that positively charged dimethylamino group of dimethylamino functionality, and all these positive charges negative charges will become neutral, and we will get the removed byproduct of urea, N substituted urea product, and in the main product is the formation of attachment of this dimethylamino functionality on the carbonyl group. Now the question in this step here, in the second step, when the lone pair of nitrogen of dimethylaminopyridine functionality was going to attack on the ester carbon, electrophilic carbon, then why it is attacking on the carbon which is further attached to oxygen, that is of ester functionality, and it is not going to attack on the carbon which is attached with two nitrogen and one oxygen, that is C double bond N functionality. If you see keenly here in this step, we have attached this nitrogen on the carbon of this C double bond O functionality, and in the formation or the pathway of the product, we have been removed with the side product of urea, substituted urea. But if this nitrogen attacks on the C double bond N functionality, then in that case first step will be easy, that nitrogen will nitrogen of pyridine will attach on the carbon of this C double bond N, and the C double bond will become single, nitrogen, the positive charge will be finished, and we will get the chloride ion counterbalancing the positive charge of this dimethyl amino group of this dimethylaminopyridine functionality. This is okay. But in the next step, what will happen? There is no bond which is going to be broken and forming a stable moiety. So this thing will never move towards that side, because the product is not stable one and it is not attaining the stability. So therefore this lone pair is going to attack on this carbonyl carbon only, and we get this byproduct of urea, substituted product, and along with it we get this dimethylaminopyridine functionality, substituted amide. Here is the remaining part of step 2, that is this protonated dimethylaminopyridine substituted amide functionality. Now the hydroxy group present in this functionality in this molecule, acting as a nucleophile, attacks on the carbon of the carbonyl group which is electrophilic in character, and oxygen gets the negative charge due to breakage of pi bond, and we get the cyclized intermediate. When this oxygen comes back, then the C double bond C single bond N is broken, which moves towards the nitrogen, making their double bond, and then the double bond between carbon number 2 and 3 moves towards the carbon number 3, 4 and 3. Double bond between carbon number 4 and nitrogen now becomes single bond, and we get the neutral dimethylaminopyridine as a byproduct, and the lactone functionality, creation of generation of lactone functionality, in which hydroxy is protonated, and this proton is removed by the chloride ion present there, and we get the neutral lactone functionality after the removal of HCl molecule from this functionality. So this is the overall formation of lactone by using Keck Macrolactonization process, and the more simplest mechanism has been described here in 2 steps. Here are some general features of this Keck macrolactonization process. First is point that, as with other macrolactonization procedures, the reaction requires high diluted conditions, that is less than or equal to 0.03 molar condition are enough for the formation of the product or the progress of the reaction. Second, the substrate is usually dissolved in an aprotic solvent and added to refluxing solution of reagents via a syringe pump in several hours. That is, this hydroxy carboxylic acid, which is a substrate, is dissolved first in aprotic solvent, and then it is added to the refluxing solution of the reagents by a syringe pump in several hours. That is, it is added drop wise, slowly. Next is the activating agent here used is N dialkyl carbodiimide, which can be DCC or EDCl. EDCI. that prevents small amounts of water from destroying the activated acyl derivative. The process is essentially self-drying also. This carbodiamide reagent is typically used in several fold access to ensure high conversion of the starting material, that is to convert the starting material substrate into the product. To increase the yield of the reaction, we have to use this carbodiamide in several folds than that of the starting material or substrate. The use of the dimethylamminopyridine HCl, that is protonated amine, prolongs the lifetime of activated acyl intermediate and so suppresses the formation of undesired N-acyl-urea byproduct. So dimethylamminopyridine HCl is recommended for the progress of the reaction also, and we have discussed in the introduction section of previous lecture that without using DMAP.HCl, Keck and scientist was unable to get the electron by using the esterification process. There are some disadvantages also related to this Keck macrolactonization process. The first disadvantage is, as we have discussed, that it uses the excess amount of dicarbodiamide reagent for the conversion or for the better yield of the product. And also at the end of the reaction, this excess carbodiamide has to be destroyed by using acetic acid or methanol, and so the byproduct has to be separated from large amount of dialkyl urea, because the hydrolysis, the destruction of by using acetic acid and methanol, the destruction of carbodiamide will result into the formation of dialkyl urea, and this there will be a large amount of dialkyl urea from which the product has to be separated. One modification has also been recognized for this Keck macrolactonization process, which is just the use of the polymer bound DCC, that is instead of using simple DCC carbodiamide, dicyclocarbodiamide, they used polymer bound dicyclocarbodiamide, and this polymer bound DCC was used for the simplification of the process or simplification of the workup at the end of the reaction. Here are some synthetic applications of this Keck macrolactonization reaction, which has been used for the synthesis of some natural products and also some drug molecules which have been used for different diseases like antifungal, fungal diseases, microbial diseases. Here the first example you can see here. The blue color part of the molecule is showing the COOH carboxyl functionality, and the red color part is showing two hydroxy group are there, but the hydroxy group at the end of the chain is looking to be stereochemically approachable for the formation of cyclic ring. So therefore this hydroxy attacks nucleophilic attack on the carboxyl functionality during the reaction, and we get the cyclized product lactone functionality. The reagents used for this reaction are DCC2 equivalents, DMAP3 equivalents, DMAP.HCl2 equivalents, and in chloroform as a solvent. Slow addition of substrate was performed, and also in about 11 hours on reflux, and we get the final product with yield of 59%. Second reaction shown here is also involving this Keck macrolactonization process. Here you can see the in blue part, at the end of the blue part or blue chain, you see COOH carboxyl group, and in the red chain there are looking to be two hydroxy group. And after the cyclization process, the first step first hydroxy group is looking to be approachable to this functionality and stereochemically approachable, so therefore we get the cyclized electron functionality from this first hydroxy. After this first step, formation of electron, this region has been further moved towards the step number 2 on interaction. This first step was with 65% yield. Then the second step was the interaction with toluene sulfonic acid in methanol, and a product was 86% yield. And in the third step there was the interaction with mercuric chloride calcium carbonate in acetonitrile water 3:1 ratio solvent, and we get the 85% yield of this final product. Here I am not going to discuss what happened when these two steps number 2 and 3 were performed. We are only focusing on our step number 1 Keck Macrolactonization process. Here you can see the R group have also been shown in the first rectant side of the second reaction, and it is written here that R is equal to TBS. TBS is an abbreviation which has been used for the tertiary butyl dimethyl silane ethers of silicon, silane ethers, and which are mostly used as protecting groups also. Here is the third example of this Keck macrolactonization reaction. Here you can see the blue part having a carboxyl group and the red part having hydroxy group. After using the basic regions, that is DCC 6 equivalents, DMAP 7 equivalents, DMAP.HCI 6 equivalents in chloroform on reflux for 21 hours, and the yield was only 39% for this region, and we get the cyclized electron, and after a number of steps it was converted into the drug molecule of epicularin A. Next is the formation of carboxyl electron. Here you can see the molecule in blue color with bearing carboxyl group in the second reaction, and the red part of the molecule at 15th number carbon has hydroxy group. This hydroxy group interacts with the carboxyl acid carboxyl group, and we get the cyclized electron. After a number of steps, mean first step is the formation of electron, then second step is the interaction with hydrofluoric acid in THF, tetrahydrofuran, room temperature 96% yield, and third step is the reaction with metachloroperoxybenzoic acid 1.5 equivalents in chloroform 18 degrees C with in 5 hours, and 81% was the yield. Then we get the final drug molecule of apothylone B. Here you can see the OR group at 3 position of reactant is now converted into hydroxy OH group at 3 position, and similarly OR group in red color part has now converted into hydroxy group. These are the TBS tertiary butyl silyl group which were forming the ether linkage with this oxygen, and acting as a protecting group, and in the product side these protecting groups are removed and we get back the hydroxy groups here. Hydroxy groups are protected here because we are involving the interaction of carboxylic acid with the hydroxy for the formation of electron. So these hydroxy groups are blocked by a protecting group so that there may be no minimized side products or no side products at all. Here in this reaction a 9-membered cyclic ring of electron has been created by using different regions. Almost the basic structure which is involved in the formation of 9-membered ring is just similar, but the substitution has been inserted on this basic structure to compare the yield of the product. Here you can see at the bottom the basic unit which is treated with EDCl, DMAP, DMAP, HCl, chloroform and solvent 65 degrees C temperature, and the product should be this 9-membered cyclic electron, macrocyclic electron, but the yield was 0%. That is, this reagent did not convert into the product. But when there was substitution of here you can see at the hydroxy group bearing carbon, then there was a yield in the similar condition of 24%. But if there was substitution on the acidic part also with the methyl or with the tertiary butyl silyl ether, then we get the product with 78% yield. This thing explains that the substituents have a great role in the formation of the product, in stabilizing the intermediate, in stabilizing the reaction progress, and initiating the reaction progress. So the substituted electrons are easy to form as compared to unsubstituted electron. So there is a great effect of the substituent on the nature, on the yield of the product. Here is a comparison of the formation of electron of carbohydrate type functionalities bearing a number of hydroxy groups. Some of the hydroxy groups have been protected, but 3 hydroxy groups, so you can see in the rectangle, are open for the reaction. First product with 24% yield is the with one of the hydroxy group at the top of the molecule. Here you can see on the rectangle side there are 3 hydroxy group in the mid of the molecule. 2 hydroxy groups are present on the same ring, and third hydroxy is present lonely on a single ring. When there is one product with 24% yield in which acid is now attached with this lonely hydroxy group, and the 2 remaining hydroxy groups remains intact. But 28% product yield has also been obtained in which this carboxylic acid functionality has interacted with the one of the hydroxy group of the among these 2 present on the same ring, and this hydroxy group is from the outside of the ring, outside of the chain, which is stereochemically approachable, and so yield is product is found with this hydroxy group. But the other hydroxy group is not interacting with this acid functionality, and there is no product regarding this hydroxy group. Here is the last example of synthetic applications, in which you can see there are 2 hydroxy groups in this rectangle molecule and 1 acid functionality. One hydroxy group is present at the vicinal position of carboxyl group, and the other hydroxy group is present at the end of this long chain molecule. So the second hydroxy group, which is present at the glucose cyclic ring, 6-membered cyclic ring, is stereochemically approachable for this carboxylic acid. So by using the basic conditions, we get the 53% product in which this carboxyl group is interacted with this hydroxy of 6-membered cyclic ring instead of the vicinal hydroxy, because it will be more less stable product. Although 3-membered electron are known, but as we have discussed in the start of this lecture, and also in the I think previous lecture, that the formation of small rings, alpha electron or beta electron, is looking to be impossible because of less stability and high reactivity of these species. So this is all about of the Keck macrolactonization process reaction, and thanks.